So welcome everybody. I'm very happy that we have for this Friday seminar Richard Booth with us, who will speak about protoplanetary disks. And to briefly introduce him, he did his undergrad in Cambridge until 2010 with Kathy Clark. Then like his undergrad thesis with Kathy Clark. Then he did a PhD in Oxford from 2010 to 2014, but this on supernova progenitors. Then he went back to Cambridge for a postdoc until this year, where he worked also on protoplanetary disks, and he will show some of his work today. And since October from this year, he is a postdoc at Imperial in London. So, Richard, the screen is yours.
Thanks for the nice introduction, Caroline. So can you all hear me well enough and see my slides and everything? Great. So I'm going to talk about three or so different bits of work that are all related to something I've been interested in and working on for the last few years, which is sort of the evolution of gas and dust in protoplanetary disks, and how that links to the composition of the disks, the stars, and planets and stuff like that. So we've got three different topics here. I'm not sure whether we'll have much time to go through the last one, so if not, I'll skip over that. So let me know how I'm doing for time, please. Okay.
Yes, I will.
So these are the broad topics are sort of looking at the evolution of dust in protoplanetary disks and how that's going to impact planet composition, trying then to use latest observations from ALMA and accretion rates to understand just exactly how efficient these processes are. And then finally, I'm going to talk about the solar refractory depletion. So the sun is missing sort of 10% of rocks compared to solar-like stars, and I think that that's due to the formation of Jupiter creating a transition disk. So hopefully we'll get time to talk to you about that as well. Okay, so a lot of the motivation for this, for me getting interested in this stuff, comes from studies of exoplanet atmospheres. So what I'm showing here is a plot from Brewer et al. 2017, who is showing what was the state of the art then in terms of the C/O ratio of some planets measured and compared to the C/O ratio of the star. So at that time, the individual measurements were pretty uncertain. So this dashed line of 1 would be the planet's composition appears to be the same as the star. And lots of these planets were, essentially consistent with that value, but with a lot of scatter about it. But when you looked at the average, you could see the average was sort of hinting at an increased C/O ratio in the planets. This is still very uncertain. It's actually probably still uncertain today whether the bulk composition of the planets are significantly different to the stars on average for exoplanets. But I got interested in this and interested in what we can learn about this kind of stuff from looking at protoplanetary disks. At the very simplest level, you can understand the composition of a planet in terms of the amount of gas and the amount of solids that it's accreted. So what I'm showing here is two plots. On the left, it's essentially the C/O ratio of gas and dust in a protoplanetary disk from Karen Oberg in 2011. And this is sort of a semi-empirical model where the total composition of all of the gas and dust across the disk is assumed to be the same, but volatile species will be partitioned out either in the gas phase or on the surface of icy grains, depending on temperature. So as you go further away from the star, the disk gets colder, so more and more volatile species subsequently freeze out. That process leads to an enhancement of the C/O ratio of the gas, but a decrease in the total metallicity of the gas because you've locked up some of those metals into solids. And then the solids always have a C/O ratio that's lower than that of the gas. So what Madhu did in 2014, and I think other people have done this before, is essentially you say, take a very simple model for a planet where I build it up with some quantity of solids and some quantity of gas and see what composition I get, depending on where I form it in the disk. So if you And you get this plot on the right-hand side, which is compositions in the plane of O to H on the x-axis and C to H on the y-axis. So if you think about starting with a planet that's 100% gas, then that's going to put you in this bottom left quadrant, where the data is in the bottom left in this one small eighth of the diagram, because you have a C2O ratio that's greater than solar, so you're above this dashed line, it goes diagonally up, but you have a C2H and an O to H that's below solar. So if you then mix in solids, you move up and to the right because you're getting more metal rich, but you also cross that C2O ratio of solid lines. So essentially, these, by these very simple arguments, you expect planets in basically these two corners, and it sort of doesn't really matter how you form the planets, right? It doesn't matter whether you form them from big things or small things, or you accrete gas first or the solids first. By this argument, the bulk composition is just going to be some sum of gas and dust, and going to lead you into these corners. If you want to link that to the actual observed metallicity of the planets, then that becomes much trickier. You actually have to worry about the distribution of elements through the planet, metallicity gradients, things like that. And doing a better job than something like this turns out to be a very difficult problem. So the models in this figure here are essentially for classical core accretion. A few years later, Madhu then revisited it using Bertram Bitz's pebble accretion models. And essentially, as I alluded to, you're going to get the same answer. You get gas-rich planets down here. And if you add some solids into the planet one way or another, Madhu assumed they'd come from the core in this paper, then you'll populate the upper right panel. If you want to change the composition of the disk, so you can change the composition of the gas and solids, you have to wait a long time, okay? So this plot on the left-hand side is from Christian Eistrup, and this is what the C2O ratio looks like after several million years of disk evolution. It has broadly the dashed line here is the gas, again, so it needs to be compared to this solid one. The numbers are lower because he started with a lower initial C2O ratio, but you have the same kind of shape, and you have to wait for a very long time for the enhancement of the C2O ratio of the gas to disappear due to chemical reaction, sort of 5 to 10 million years. And by that time, we think most planet formation is over. So what I got interested in was that these pebble accretion models that Madhu used in this paper actually require dust in protoplanetary disks to be big and to drift. So if we go back to sort of the classic papers, so this is from Weidenschilling on the left, 1977, who showed that the radial speed of velocity through a protoplanetary disk depends on the size of the dust grains. So for at small sizes, the radial drift velocity is increasing up to some maximum size, and then it decreases again. And this peak is at a size around what I call the Stokes number of 1, which is where the drag force, the time that the drag force acts, that stopping time, is equal to the local Keplerian frequency. So most particles in protoplanetary disks are going to be on this left-hand side, so the bigger particles drift more efficiently, okay? If you put this into a model for the evolution of the surface density, so the one on the right here is for a fixed grain size from Yudin and Chang, then essentially dust grains drift in, enhancing the surface density in the inner disk and depleting it in the outer disk. Okay, so that's kind of the basic physics of radial drift. If we then couple it with what's going on in the composition of the disk, we can sort of understand qualitatively how it's going to affect the composition of the disk. So we have this picture, for example, of a CO snow line, and inside that snow line, CO is in the gas phase, and in the outside, it's frozen onto the grain surfaces. So the first thing that happens is these grains grow until they reach large enough sizes that they begin to decouple from the gas and drift in. As they drift in, they're going to cross the snow line. And as they cross the snow line, they then sublimate, releasing CO gas into the disk. Right? So you get this region inside the CO snow line of an excess of CO vapor high C2O ratio, high C2H ratio. So high metallicity gas with a high C2O ratio that was not present in the models in the disk initially. So here you could have high C2O ratio, but you would have a low C2H ratio. So if you then look back at the picture I showed before from Karen Oberg, where we have now multiple snow lines, H2O, CO2, CO, and in each one of these snow lines, we can sort of expect a peak in the abundance of each of these species. And that's going to change, for example, the C2O ratio. Okay. So what I then did was I took a sort of a simple model for a protoplanetary disk, which is what you consider more or less to be the state of the art of our understanding of how gas and dust evolve in disks at the moment. So it's a simple model for the gas, which is viscous with grain growth and radial drift. So the grains grow on a timescale of a bit less than 1 million years and start to decouple and drift into the inner disk. And as they do that, they cross these snow lines. So in the bottom left panel, you can see the carbon to hydrogen ratio is a function of radius, and the lines going down this axis is time, right? So you get these peaks at the snow lines initially, and then over time, as the dust to gas ratio drops and the amount of supply of dust and molecules decreases, then these peaks start to get diffused out by diffusion and transported through the inner disk through accretion. If we look at this in terms of C2O ratio, the outer disk has a very high has a C2O ratio of 1, which tells you that what we're mostly seeing is CO gas. And then as time goes, initially in the inner disk, the C2O ratio drops because you're depositing lots of water in the inner disk, but that water then accretes onto the star, and then the C2O ratio starts to climb. And at the end of this simulation, you have a disk which is more or less dominated by CO. So the abundance throughout the whole disk is getting towards 1. Okay. So these models were quite simple and didn't include chemistry. And I'll come back and discuss what actually including chemical reactions does to this picture. So in these models, we assume, for example, that if you have a molecule that's CO, when the disk is formed, it stays CO as a CO molecule throughout the whole disk's lifetime. But in reality, we know that that's not the case, and chemical reactions can change species from one form to another. But before that, I'll discuss how this kind of behavior is a bit sensitive to what we assume for the underlying disk distribution. Okay, so what I'm showing here is the C2OH ratio for models with 4 different values of the turbulent alpha parameter. So the alpha parameter sort of, you can think of it as a number which quantifies how strong the turbulence is in the disk. And turbulence does several things. It drives diffusion, it drives accretion through angular momentum transport, and it also causes grains to hit each other and fragment. Okay, so increasing alpha is having 2 effects. It's making the gas accretion more efficient, and it's making the dust grain smaller, so radial drift is weaker. So if we go to very strong alpha, we can see that for the radial drift of dust grains is weak, and and essentially the evolution of the disk abundance is relatively small. Okay, but then at very weak alpha, you get the opposite. You get very strong peaks in carbon to hydrogen ratio, and they live a long time. It takes a long time for accretion and diffusion to weaken those peaks. So again, several million years. Okay. So this is sort of one aspect of understanding the details of this problem. How efficient is radial drift is going to be key to really understanding what happens at these snow lines and whether we see strong enhancements or weak or no enhancements at all. And the other aspect I'll come to is the chemistry. So I actually at the time took these models and ran them through simple planet formation models, and those are the blue points, which show that you can get essentially a wide range of metallicities at C2O ratio of 1 these are for gas giant planets that cross the CO snow line essentially. And again, getting a high metallicity in a C2O of 1 is a bulk. It is difficult with the old models, because with the models without radial drift, because the solids have low C/O ratio. So you need to invoke some process within the planet or in the disk to be able to remove the water to get up into this region of the diagram. So planets in this region of the diagram could well be signatures of formation in a radial drift dominated disk. Okay, so the thing I did after that was then try to take these simple models and add in a chemical network. So I did this working with John Eiley. So John Eiley has been for a long time doing models of protoplanetary disks, thinking about and looking at their chemistry. So he has this code that he was using, for example, for simulations of self-gravitating disks, which are shown up in the right. So has sort of about 100 different species, 1,000 different reactions, and it's designed to sort of follow the gas phase chemistry of the main constituents like CO, CO2, water in protoplanetary disks. His code is designed for sort of disk midplanes. It doesn't really do UV and things like that, but that's fine for what we want to do here for the bulk of the abundances. So we took John's code and essentially updated it to modern rates and things like that, and coupled it with my disk evolution model to see what, how essentially the chemical evolution of the disk will compete with the radial transport. Great. So what I'm showing on the left is on this slide is essentially some tests of that code that we developed, showing on the left the code we developed with John, and on the right sort of the benchmark model from Christian Eistrup. So these models should be the same. Christian's chemical network is enormous. It's one of the biggest there is. It includes many, many, many species, lots of gas phase reactions, lots of grain surface chemistry. And on the left, we've got the simpler model here. So our simple model does actually capture, in a sense, the main physics that's happening on 1 million years, which is, for example, the depletion of methane, which you can see in both models. The timescales are fairly similar. They can differ by a factor of 2, which in this sense is actually not too bad. The main way that they actually differ on long timescales is that on timescales of sort of several million years, Christian's network has a depletion of CO gas in it, which is much weaker in John's code, mine and John's network. And the reason for that is that this is a grain surface driven process, and we haven't yet updated the code to include that. So we looked at essentially the first 1 million years, where we would say, okay, the differences between the chemical evolution that we'd expect with our code and with a full detailed model should agree relatively well. Okay, so what I'm showing here is essentially how chemical reactions are going to affect the composition of a disk without any radial drift. So essentially, this is what happens if you assume the gas and the dust move together through the disk, so that every parcel of gas always has the same composition. And the models on the left are sort of equivalent to what you would get, what's typically done in the literature, which is you take a static model of the disk and you just compute the chemistry at every location as if the disk wasn't moving for, say, a few million years, 10 million years. And then people want to compare these to observations or planet composition and stuff like that. So we did that, and the initial composition is the blue line. And the main thing that happens in this model is that you have this region between 2 and say 20 AU, where methane's originally in the gas phase, and it gets depleted. It gets turned into essentially larger hydrocarbons, and it becomes missing from the gas phase. It freezes out onto the surface of the grains. So after sort of 1 million years or so, you're left with more or less CO-dominated gas all of the way in to a few AU, and then all of the other species are frozen out onto grain surfaces. As you increase the rate of transport, so this is now adding in advection of gas and dust together, moving left and right, then you start to weaken this process. And for strong transport, you can actually move the gas parcels through this region on a shorter time scale than the chemistry can act. Okay, so that then prevents essentially any significant changes to the chemistry, and you're left with a composition that looks more or less like the initial conditions at all times. Okay, so we can see in the models without radial drift, there is kind of a competition between transport and chemistry going on. If we then add radial drift, we start to see a different picture. So the left-hand panel now here is the full physical model. So it's got grain growth, radial drift, viscous evolution, and things like that. But the chemistry is done very simply. Again, it's back with the original assumptions that there's no, that a CO molecule is always a CO molecule. It can just freeze out onto grain surfaces or adsorb. And the results here look, pretty similar to what we had originally. There are some small differences because the abundances we assumed for our initial conditions in this model match what we used in Eistrup's paper rather than match what was used in Madhus's paper. But we have the same kind of picture that you dump lots of material at the CO snow line, and then it gets evected in slowly over time. The next panel is then adding chemical reactions and adding chemical reactions to this picture for exactly the same model. That's all that's different between the left and the middle panel. And you see that there are some differences, but you still sort of have this same picture as before, that you quite efficiently create strong enhancements in the C/O ratio and in the carbon abundance at the snow lines. It's the methane snow line, not the CO snow line. You get these strong carbon abundances. There is some depletion due to chemical reactions, and essentially what happens is that you convert methane to larger hydrocarbons like C2H6, which then stay on the grain surfaces for longer and then pop out further in the disk at a couple of AUs. So you get this narrower but higher spike in the inner disk. And then the right panel is the same kind of thing, but now with a model with an alpha of 10 to the minus 2. And this model now looks much more like the model that didn't have any radial drift, right? The grains are small, and you don't get very strong enhancements of the carbon abundance in the gas phase either. This looks a lot like the model we had on the previous panel with chemical reactions and strong transport. So the summary of this is that actually really to understand how strong enhancement we're going to get at snow lines and whether we have these regions of these narrow regions of high C2H and C2O ratio gas is really a question of how efficient is radial drift in disks, more than it is a question of how strong is the chemical evolution. Essentially, we think that planet formation and radial drift and a lot of these things will have done a lot of its work in the time scale in which the chemistry can actually do a lot to the disk composition. So that's what the next section of my talk is going to be about, essentially trying to understand, should radial drift look more like the models in the middle panel, or should it look more like the models in the right panel? And that's work I'm doing at the moment. Okay, before we do that, it's worth commenting that there have recently been claims of evidence that radial drift may be enhancing the carbon abundance or the CO abundance in protoplanetary disks. So these are some results from Zhang et al. And what they did was they looked at the CO lines in the disk HD 163296 and derived a profile of essentially the CO abundance as a function of radius in that disk, where the CO snow line is. And you could see a drop in the CO snow in the abundance across the CO snow line. That in itself is an effect essentially of just the CO molecules freezing out onto grain surfaces. But what they noticed that was interesting is that the CO abundance in the inner disk is actually higher than the CO abundance you get looking at the material, the carbon abundance that you get looking at the material that's accreting onto the star, okay? So they argued that this means that there must be some actually extra source of carbon that's arriving at the CO snow line, and that's probably, so that's his R3 model, and that's probably due to radial drift. When you look at the errors, this is only kind of a 1 sigma result with relation to the stellar C2H abundance. Because the carbon abundance of the star is fairly uncertain. But they argued in their paper that, well, okay, it's only, you know, 1 sigma above the stellar abundance, but then normally in a protoplanetary disk, you wouldn't expect all of the CO to be, so all of the carbon to be in the gas phase, right? So in the ISM, sort of 50% of the carbon is going to be in carbon grains and another 25% in CO2. So they argue that you'd expect maybe normally 25% of the carbon in CO, and then argue that that would be evidence for a pretty strong enhancement. And sort of a more pessimistic argument, they said, is okay, you've got half of the carbon in grains and a smaller amount of CO2. And they suggested that they didn't think that you ought to have much more than, say, 50% of your carbon in CO. And then, so this is still a factor of 2 or 3 enhancement of the CO abundance at the snow line. So this is still pretty tentative evidence. It's only 1 disk, and it's not terribly significant. It's statistically significant at the moment, but it's interesting that there's now potential evidence that radial drift might be going on in disks and might be transporting volatiles. Hopefully with the data that's coming out of the MAP survey, we'll know more about that in the coming months and years. Okay. So moving on to the second part of my talk, it's kind of answered this question: how fast is dust evolving in protoplanetary disks? So to do this, we can compare essentially models, like the models I was using before, to observations of protoplanetary disks. For example, their masses, their radii, their accretion rates. Since ALMA, we've now got surveys of protoplanetary disks in a wide number of regions. So these surveys are all at 1 millimeter. In regions from like Taurus and Lupus that are about 1 million to 3 million years old, to older regions like Upper SCO, which is 5 to 10 million years old. These surveys are essentially complete. There are some upper limits, but all of the stars have been surveyed. So they're a nice sample for trying to understand how or why dust is evolving in these disks. So maybe one of the first attempts that we tried to do this with was a paper by Giovanni Rizzotti, where we used my code to look at essentially the flux and radii of protoplanetary disks, and compared them to some data that Sean Andrews had used to derive this correlation, which is this blue line in this blue line with a region around it is the sort of the 1 sigma contours that they derived from data in Lupus, and I think it was Ophiuchus as well. So what we realized is actually that the radial drift limited models, which are the models with low alpha, actually have a slope, this orange slope, which is meant to be close to the observationally derived slope. This is a theoretical plot at the moment. Whereas the highly turbulent models should have a different slope and maybe don't match the data as well. When you then actually do the comparison between flux and radius, I think it's a little bit less clear. The drift-dominated models do actually do a very good job, which are these circles, do a very good job of explaining the observations. But the fragmentation-dominated models aren't so far off. There may be a factor of 2 or 3 too high in flux, and there's enough uncertainty on the opacity that you could argue that, you know, maybe the opacity is a bit lower, and then these models would match the flux radius correlation too. We've since looked at that again for regions of different ages. So again, this is flux on the y-axis and radius on the x-axis, and this is more or less the same data for Lupus at 1 million years, and then Upper SCO, which is an old region, at 5 to 10 million years. So the models do a reasonable job of explaining essentially where the data sits in these planes at both 1 to 3 million years and 5 to 10 million years. And again, these are the radial drift dominated ones. However, so the solid parts, the thick parts of these lines are the regions of these curves. So this is a track in disk evolution space. A single disk moves through the space like this. And the solid lines denote where the disk is, you know, where the models sit at an age of 1 to 3 or 5 to 10 million years. So you can kind of see that at 5 to 10 million years, we're kind of missing a population of disks here, which could possibly point to multiple populations or some younger disks in upper SCO. But it's also possibly the case, or likely the case, that these models predict that dust evolution is a little bit faster than might actually be the case, right? That, if dust evolution is, say, a little bit slower by maybe a factor of 2 compared to what's going on in this model, then you'd do a better job of explaining these data points with small radii. But I was actually surprised looking at this that the models actually do a reasonable job. I sort of expected them to be terrible, based on the argument that the dust evolution that goes into these is really fast. 80% of the dust is reached the star in much less than 1 million years, for example. But even with that, they're not actually vastly in disagreement with the observations, because although the dust evolution starts off fast, it actually slows down, and between, say, 1 million years and 10 million years, the dust evolution in models is quite slow. So another way to look at this is actually in the gas mass and accretion rate plane. So this is something that Giuseppe Lodato and Heath Mulders have looked at using gas-only models. So if you just take a gas-only viscous evolution model, it's sort of very hard to explain the scatter in accretion rates in lupus. And you can do that if you play around with the disk parameters enough. You play around with, for example, the strength of turbulence, the disk sizes, things like that. You can just about get them to match at the age of lupus, but it becomes even harder for older regions. If you then put the dust evolution, again, using exactly the same models we used before, the radial drift limited ones, the models do essentially a better job of explaining the data that the gas-only models miss. So dust evolution is potentially an important part of explaining, why these data look the way they do. But if we use the models just as they were, just including viscous evolution and radial drift, we have a problem that they predict, for example, a population of very low mass disks with significant accretion rates. Which aren't seen, right? And then there's also an issue that they struggle to explain the most massive disks too. So what I'm showing now is the older region, which is upper SCO, 5 to 10 million years, which has essentially very similar masses and very similar accretion rates to what you see in lupus, but lower masses. So it's moved to the left. And the viscous-only models now essentially completely miss the data entirely, but the models with radial drift again are doing a relatively good job of matching the data. Again, apart from this population of disks with high accretion rates and low dust masses. You can get around the problem with low accretion rates if you invoke photoevaporation. So we think that disks don't evolve just viscously. There might be MHD winds. There might also be winds driven by a high energy radiation. So the models we used in here were X-ray driven winds or extreme ultraviolet driven winds. And essentially what happens in those models is once the accretion rate drops below a threshold, which is roughly, essentially the accretion rate drops below the mass loss rate due to the wind, then photoevaporation starts to open up a gap in the disk, and it stops material accreting onto the star. So that removes this population of low mass disks with significant accretion rates. So we think that that's what's going on. That photoevaporation is explaining what's going on with these low mass disks late in their lifetimes. But again, we still, for example, lupus and also maybe in upper SCO, have this subpopulation of relatively massive disks that it's difficult to explain with the models. Then we have tracks going through this region of parameter space, for example, but they don't spend enough time there, right? They leave this region after a few tenths of a mega year. Okay, so there's definitely work to be done to try and understand why these most massive disks, which are maybe the most interesting ones for forming giant planets, sit, apart from where the models actually are. That's telling us something about the dust evolution. We can get, a better picture of what's going on. Okay, so that's just me highlighting that. Another problem we need to understand is the grain sizes. So this has been known for a long time. So on the x-axis, so this is a plot from Tilburn steel. On the x-axis, you're showing the millimeter flux, and on the y-axis, it's the spectral index. So the spectral index is essentially the log of the slope of fluxes between 1 and 3 millimeters, and it's a proxy for grain size. So large spectral index is small grain size. And this is another place in which the models fall down. Although they get the radii of the disks right and they get the masses of the disks right, they predict that the grain sizes, as the models evolve, should be larger than essentially what's inferred from the observations. And that's larger by maybe a factor of several, to maybe 10. So we need to understand, why do the disks appear to have larger grains than what the models are predicting. Larger grains would suggest that dust evolution is faster than we're getting in the models, or perhaps that some dust trapping is going on. Okay, it's worth noting, however, that this plot is actually somewhat biased. So this is a recent figure from Marco Tazzari's paper. He was doing more or less the same thing, measuring the spectral indices for disks in Lupus. And what I'm showing here is essentially all of the disks in the Lupus survey and the ones that they surveyed at 3 millimeter. And this is with ALMA. This paper from Till was pre-ALMA days, where the data was even less sensitive than you can do with ALMA. So the ALMA data essentially is limited to the brightest 50 or so % of the disks. And before that, it was probably even, it was even higher. So the disks that we're struggling to reproduce the mass of in the first place are also the disks that we don't match the spectral indices of. So I'm interested to know whether essentially what's going on in these disks is something like dust trapping. So if I move on, we know that the most massive disks have structures, okay? And these structures, probably trapping dust, and they're probably changing how dust evolution. So we maybe have this picture where these most massive disks can have large grains because of dust traps, and maybe the smaller disks are actually evolving due to radial drift. At the moment, we don't necessarily know the answer to that question. That's one thing I want to try and get at in the coming time. It's not super clear that dust trapping will solve all of our problems. If you look, for example, at the recent paper by Paula Pinilla, that it's actually difficult to add dust traps into a dust evolution model and make it match the observations. It doesn't naturally want to go in the direction, in the right direction of matching the observations. Yes, you keep the dust masses higher, but you also get large grains, and you don't necessarily sit in the right region of flux, radius, and grain size parameter space. So there's a good amount of work to do to understand this, and this is kind of the next thing that I want to do in this area. Okay, how am I doing for time?
You have 10 more minutes if you want.
Wonderful. Okay, so I've got move on to the final project that I wanted to talk about, which is the refractory depletion in the solar twins. Okay, so this has been known for 11 years now, maybe longer. On the left is a paper from Jorge Melendez, and what is showing here is the difference between the sun's abundance and the average abundance of his sample of 11 solar twins for a range of elements that they measured, and that's been plotted against condensation temperature. So condensation temperature here is the temperature at which those elements tend to freeze out, so they go from being in the gas phase to being in a solid locked up into dust grains. And essentially you notice that the sun, compared to the solar twins, has a depletion of refractory elements, okay? His definition of a solar twin here is a sun with a very similar mass, temperature, metallicity to the sun. So these stars all have more or less the same metallicity, and these abundances are normalized to iron anyway, so that should be removed. So we saw this result, and that was very interesting. There's been lots of proposed explanations. More recently, Megan Bedell looked at the issue again, now with a sample of more like 100 stars, and she saw still a very similar effect, that the sun is depleted in essentially a bunch of rock-forming elements. It's not so clear from Megan Bedell's work that it should be a slope rather than just, you know, a bunch of elements that are not very depleted and a bunch of elements that are more strongly depleted. But it's clear that the depletion in some sense is real. And I was interested in the origin of this. So the original explanation for this trend at the time seen by Jorge Melendez was put forward by Chambers, who suggested that if you mix 4 Earth masses of rocky material, so a combination of chondritic and Earth-like material into the solar convection zone, then you could essentially flatten this curve out. You could reproduce. So he argued that you can reproduce this curve if the sun is depleted in, say, 4 Earth masses of rocky material, or equally all of the solar twins have swallowed 4 Earth masses of rocks. So that argument was based upon the fact that the sun's convection zone today is something like 2.5% by mass. So if you scale that up to the whole size of the sun, because when the sun is young, when stars are young, they're fully convective. So any missing material is going to have to be mixed through the whole sun. So if we want to look at formation early on if we want to look at processes early on in the sun's evolution, the sun will be fully convective. And that number 4 Earth masses then turns into more like 150 Earth masses. So we're interested in explaining this trend. And to do that, we took the disk evolution models, a bit like the ones I've described before. So gas evolution, dust evolution, photoevaporation, and combined them with a model for the evolution of the sun's convective zone to work out what the depletion of the sun's convective zone should be. You can do that and ask the question, could this effect be due to rocky material? And we now know enough about exoplanets to know that actually rocky planets can't really explain this. Most stars have more rocky planets around them than the sun, so it sort of doesn't make sense to associate this depletion with the formation of the Earth, for example, because you'd expect the sign to be the other way, right? You'd expect most stars to have a stronger depletion than the sun, whereas here the sun is the one that's depleted rather than the rest of them. So it's hard to reconcile this with the formation of rocky planets, but we think instead that the formation of giant planets will work better. So what I'm showing here is essentially a disk evolution model. The solid line is the gas, the dashed line is the dust. Same kind of model we had before, apart from 500,000 years, we put a planet in it that then opens up a gap. That gap opening traps dust outside the planet's orbit. And over time, the accretion of dust onto the star then decreases. Because gas is able to cross the planet's orbit, the accretion of gas onto the star continues. And that means that the star's photosphere over time is going to get more and more depleted. And eventually in this model, at around 10 million years, photoevaporation kicks in and opens up a gap in the inner disk, shutting off the accretion of gas. So that's what's going on there. Okay, and this is the same model. This is the same model, but now without a planet. So for comparison, dust is continuing to accrete onto the star for essentially the whole time until eventually photoevaporation kicks in and depletes both the accretion of gas and dust at the same time. So our hypothesis here is that essentially the difference between these models with and without a planet, without a giant planet opening up a gap in the disk, could be the reason why the sun is depleted, right? So if you form a giant planet, you trap dust in the outer part of the disk, and that gives you some level of depletion on the star, okay? And we know we have a giant planet in the solar system because we have Jupiter and we have Saturn, and they together can definitely create a gap in the disk. Okay, so what I'm plotting here is the metallicity, the star's metallicity normalized to, so that 0 would be essentially if all of the gas and dust was accreted equally. For models with different lines of different X-ray luminosities, and different panels are different growth rates of the dust. So the canonical models are the one in the left-hand side, and then we've slowed down growth by a factor of 10 and 100 as you move along. Okay, so photoevaporation itself leads to the composition of the star being enhanced by some amount, and that's essentially because the evolution of dust is faster than the evolution of gas. So you accrete, by the time that photoevaporation kicks in and shuts off the accretion of dust and gas, you've accreted essentially 100% of the dust, but you've only accreted, say, 80 or 50% of the gas, depending on how efficient photoevaporation was. So that gives you an enhancement in the metallicity of the star, which is kind of our baseline amount. It's nice that photoevaporation alone doesn't introduce a particularly large scatter in the abundance. We get some offset, which is different depending on how efficient dust evolution is. But the scatter is actually fairly small and well within the scatter that we know from the abundances of the stars. So if we then put in a planet and compare, now not showing the abundance of the planet, but the difference between the abundance of a model with a planet and without a planet, I can then plot essentially this depletion. The depletion of the sun is somewhere between 0.02 and 0.04 dex, depending on who you ask. And we have no problems for these intermediate growth models with slightly slower growth than the canonical parameters to match this abundance to the solar depletion. The canonical models fall a little bit short by, say, a factor of 2. But then one of the things we can do is play around with, for example, the initial disk mass. These models all assumed an initial disk mass of, say, 10% of the stellar mass, apart from 1. And we and the models also assume that Jupiter formed at 500,000 years. So forming Jupiter early means that there's more dust in the disk when it opens up its gap, and that means that, for example, so you trap more dust and you get a larger depletion. So the two things that favor a strong depletion that can explain the solar depletion are, for example, Jupiter forming early while the disk is more massive, and also slightly slower dust evolution. It's worth actually noting that the amount of mass that you manage to trap outside Jupiter in these models on the left-hand side is more like 20 to 30 Earth masses, okay? And when you look at that, that's actually a relatively small number compared to masses inferred of transition disks. So that sort of already hints towards slower dust evolution, more dust trapping, and suggests that these models, if anything, are an underestimate of what the truth should be. So with that in mind, we think that essentially Jupiter forming turning the solar system into a transition disk could nicely explain the depletion of the sun's refractory depletion. And there are other arguments that support that too. If you look at A stars in transition disks, you can see that they're not accreting as much refractory material as you'd like. If you look at sort of the fraction of stars that show solar-like depletions, that's of order 10%, which is, again, not so far away to be inconsistent with current estimates of the giant planet fraction, the fraction of stars that have giant planets. So there's a few arguments pointing towards this that suggest that the formation of a transition disk could be the reason why the sun is depleting refractory. So,
Richard, you have like 1 more minute.
So I'm done. Thank you. And I'll just reiterate my conclusion. So strong radial drift in protoplanetary disks leads to an enhancement of volatiles that can be seen in the composition of planets. This properties currently suggest that rapid evolution of dust may happen, but maybe not quite as rapid as I was using in the original models. There's still work to be done to explain what's going on in the most massive disks, and dust traps may be part of the answer there. And finally, I think that the solar refractory depletion certainly points to a transition disk created by Jupiter and dust trapping in that case. Yeah, so that's my talk and my conclusions, and thank you all for your time.
Thanks a lot for this very nice talk, Richard. So I guess there are many questions. So just for the audience, as a recap, please go to, if you have a question, go to the participants button below the window and just raise your hand. And I already see some. So Andrea, go ahead.
Yeah, thanks for a nice talk. I have a couple questions, but I'll just ask one first. I'm curious. I know that regarding the chemical evolution models, and I guess this can also apply to the dust formation models and the grain growth. I know that some of these chemical reaction rates can be really difficult to measure in the lab, and then sometimes they're still entered into reaction networks. And so I'm curious if, in the case of protoplanetary disks, the species and the reactions you expect there, are there significant uncertainties in the reaction rates that could affect the evolution?
There are definitely things we don't properly understand about chemical evolution in protoplanetary disks, and the biggest one is when you look at disks of ages of several million years, that they seem to be depleted in CO. We don't actually know where the carbon is in lots of those disks, and that can affect things. But the chemistry that's driving things that's going on in less than 1 million years is mostly chemistry of small molecules, methane, CO, things like that. And I think they're relatively well constrained. But I mean, you probably know better than I do that there can be uncertainties. And the chemistry, certainly the rate at which the chemical evolution happens in the models is all driven by ionization-driven chemistry. So it's reactions between ionized helium and methane, for example, that's one of the dominant factors there. And one of the things we don't know very well is what the actual ionization rate in the midplane of protoplanetary disks is. So even if we actually know those reactions perfectly, there's still a significant uncertainty on just how quick the evolution, the ionization-driven evolution is. That said, the rates I used there are on the high end of estimates. So if we're thinking, as we do today, that a lot of planet formation is happening in the first 1 million years or so, it's probably fair that the evolution of molecules like CO, N2, these very strong molecules, is probably not too, there's probably not too much evolution of those things.
Right. I guess I'm more familiar in the case of like supernova and nova outflows. And so in those cases, you might have higher metallicities and really weird species. And so maybe there's more uncertainties. But it also reminds me that in some of those studies, people do tend to predict larger grains than are inferred from the observations. So I wondered if that was similar.
So the grain growth models here are very simple. And I've used models here that are based upon an argument. And they do predict, they do predict grain sizes, which I think are too big. Maybe by a factor of a few. The models that you're looking at for supernovae are very different, right? The grain growth in supernovae, I think, it's actually dust formation, right?
Right.
And in protoplanetary disks, you kind of think that we have the dust grains already there, and it's more coagulation. So you have, micron-sized dust grains, and we need to understand how they stick together and fragment. So that's also a problem that is uncertain. It depends on, properties of the grains that we don't know very well, such as the binding, the surface binding energies. But it's a different kind of problem to the supernova one.
I see.
Thanks. Okay, there are more questions. Let's move to Lucio.
Richard, very nice talk, very interesting. So I have actually many questions in mind, but I will start with one and then leave it to other people. So on the last part of the talk, on the effect of Jupiter, on the dust depletion, on the refractory depletion, I was wondering, wouldn't you expect, because it is going to be statistical in a sense, wouldn't you expect also to see some systems that would be enhanced, because you might have, you know, a bigger giant planet forming maybe even earlier, and it would create an even stronger dust trap? Why don't
yes, maybe you would. To get the models for the sun to work, we actually need Jupiter to form quite early, and while the disk is fairly massive. So there shouldn't be things that are more enhanced by the sun by more than, say, a factor of 2, for example. It would be actually very difficult for us in this channel to get depletions in the sun that are much bigger than, for example, you know, what we've seen. Maybe, you know, factor of 2 or 3 or something like that. The most interesting direction there for me is actually to think about stars that are slightly more massive than the sun, because as you go to more massive stars, they have thinner convective zones, and their convective zones evolve more quickly. So if we go, you know, to stars of, say, 1.3 solar masses, then we could potentially see a much bigger signature in those stars. So that's the place that we want to go next with this, to understand how big a signature we should see in those, and whether there's anything in the exoplanet population that points in that direction.
There's a question by Judith also.
Just a follow-up regarding this early formation of Jupiter, that, you know, what happens if you form Jupiter, you open a gap, then Jupiter has to be roughly one third of its mass, so roughly Saturn mass. But what happens after? So how do you decrease so much the accretion rate? Because of course, the traditional core accretion model would show you that you are in the runaway phase, and so how do you stop that, or how do you,
I mean,
you know, prevent Jupiter to completely form up until the end of the gaseous disk lifetime?
I mean, so we don't need Jupiter to be a Saturn mass to stop the dust from getting onto the star. It's probably, you know, Neptune's not enough, but 30 Earth masses is probably fine to get the dust through. But that still doesn't get around or solve the problem that if you form Jupiter early, it's hard to explain why Jupiter is a Jupiter mass and why it's not 10 Jupiter masses, right? And I don't know the answer to that. I mean, in the models, the models don't really care whether we let Jupiter stay at a Jupiter mass or become 10 Jupiter masses. We've done essentially both models where we just say, okay, Jupiter's now a Jupiter mass. We stop it from accreting, and we've done models where we let it keep accreting, and you get more or less the same answer. There's definitely issues for understanding Jupiter's formation, its history, that kind of thing, and I don't know the answer essentially, but then I'm not sure anyone does, do they?
That's true.
Yeah, thank you. We can talk about this later in the individual discussion.
Is there actually, Richard, a trend in, for example, the Bedell abundances, that there is a difference between stars with giant planets and without?
They only have 2 or 3 giant planets in their sample.
I see. Okay.
And some of those giant planets are not the most secure detections either. And some of them agree with our model and some of them don't. So
hard to tell. Okay.
It's hard to tell, and I hope somebody will tell me if I'm wrong, so I don't waste my time. But in Megan's paper, there's a bit of a discussion of it, and it's all a bit confused at the moment.
Is there? I still see a raised hand from Lucio. Do you still have another question, Lucio?
Yes, I do. I wanted other people to go ahead first, but if nobody asks, I can ask. So this was actually more on the first part, and you emphasized the important role of radial drift in your results on the chemical evolution in the disk, but you also showed that the choice of the viscous time scale, so essentially the alpha that you put in, is very important. So I was wondering, first of all, if you try to run a model where you go to even higher alpha, which could be, you know, for the early stages, maybe when the disk is gravitationally unstable, you get up to alpha 0.1 almost or so.
So I haven't done that, but I think if you take a model with alpha, I mean, I haven't done it, but I've run enough of these models to know roughly what to expect.
Mm-hmm.
I think if you take a model with alpha of 0.1 and a high enough gas surface density that it's appropriate for example, the self-gravitating phase, you're going to essentially get relatively small grains, and your dust to gas ratio is not going to evolve too much, apart from maybe in the outermost regions of the disk.
Mm-hmm.
And so essentially, you know, the grains will grow to some size, but that size will be relatively small because they'll be limited by the strong fragmentation that you get in the self-gravitating phase. And then probably, you know, the gravitoturbulence switches off over a cooling time or something like that once the mass has dropped low enough. And then, you know, the grain sizes are going to start growing from then. And I don't think that picture would change things too much in the sense of the real thing that's driving the evolution of the models is that the growth time is larger at larger radii. It doesn't really matter too much what initial grain size you start from. Yeah. Is there anything specific you're trying to get at with that, Lucio?
No, I was also thinking about, you know, if you put it in the context of disk evolution timescales, even with your alpha 10 to the minus 2, I say the maximum case, it's likely that the higher alpha will apply to the earlier phase of the disk, and then, you know, as you go on, you might transition in a, you know, very weak alpha with you know, just MRI doing something, but we know it's not very effective until you get to the winds playing a role. And so I guess you could, you know, the plot that you showed, I could imagine that in a time sequence in a way that you might start with a high alpha phase of the disk and then go to a lower alpha phase. I don't know if we have thought about matching things in this way, you know, on a timeline kind of for the disk as a whole.
Yeah, I haven't tried to do it quantitatively, in the sense the models are probably not quantitative yet anyway, but it could certainly be done, no problem. There's nothing stopping me from actually, you know, people like Ken Rice do this, right? They put a model for the alpha due to self-gravity into a viscous evolution model, and that could be done in a very straightforward way. And I think pretty much as you say, right, you'd get to some stage when the turbulence gets weaker and then the grains are able to grow a bit more, and then maybe you go into the secondary radial drift phase and chemical evolution. I think that's certainly the picture I have in my head.
Thanks. We can keep talking more later.
Thanks also. I think from my side, yes, I think the time of the seminar is over, but there will be these individual discussions in the afternoon with you. So thanks everybody for being here. Thank you very much, Richard, for this very nice talk. And then see you soon later.
Do I have a bit of a break now, or do I have time?
Yes. So at 12 you will meet Ravid, and then 12:30 Judith.
Okay. Wonderful.
And exactly. Yeah.
Thank
Perfect.
you all for listening.
Cool. Thank you. Bye, everybody.